Okay, welcome to lecture 16. Let's get things going here. All right, we're going to talk about the direct step method in lecture 16. And essentially, that's going to be the first of the methods that I introduced. The other one's going to be the standard step method that you're going to use to basically compute the water surface profile. So we're going to talk about that. And when you look at that, you need to remember that you need to have an understanding of the water surface profile, sort of a priori, kind of know what to expect. And so I'll refer you back to lecture 15 where we did the classification of water surface profiles. There's a great flume demonstration. I didn't call it out enough in lecture 15, but if you look through, go to that flume demonstration that's part of the classification of water surface profiles and give a look at that. I think Rick does a nice job of that lecture. So if we remember from last lecture, we started out with energy, and we characterized the energy at both section 1 and section 2, looking at the pressure potential, the potential energy, and the kinetic energy, and then balancing out with the head loss. And that head loss, again, was the friction slope times L, or delta X. And we can also substitute and recognize that delta Z is nothing more than Z1 minus Z2, or you could also say that that's the bed slope times delta X. Basically, that's a way to express how the bed elevation changes, is to express it as the bed slope times the distance. Now, if I substitute those in, I can have, for delta Z, we put the S sub O times delta X. For the head loss, we call it S sub F times delta X. That gets substituted in, and what you're left with is the right side of the equation are essentially the specific energy terms. Now, if you look at this, we end up coming up with the equation. So this here up above is just a repeat of what I had on the previous slide. But we have the equation here that we know as the direct step method equation. And so what that says is, if you understand the specific energy at the downstream section minus specific energy at the upstream section, and you also know the bed slope and the average friction slope. So I want to recall this as the average friction slope, average S sub F, and we call that S sub F over bar. Okay, so you can see, let's erase some of that so you can see it better. And so this is the S sub F over bar right here. And so remember that we have the Manning equation, V is equal to 1.49 over N, R to the 2/3, S sub F to the 1/2. Well, if we rearrange that, we end up coming up with this equation to express our S sub F. And there are a number of ways to get this S sub F over bar, this average friction slope between section 1 and section 2. This is simply what I did on that example problem in lecture 15, where I basically calculated the friction slopes at both spots and just average. There's a number of other ways. There's averaging. There's geometric average. There's a simple average like this. There's a harmonic average. There's a number of different ways to get the averages. If we look at the direct step method solution, you perform it on multiple reaches of a channel, and you progress step by step. And the computations go upstream for subcritical flow, and they go downstream for supercritical flow. Why is that? Because subcritical flow, the control is downstream. So for subcritical, the control is downstream. For supercritical, control is upstream. And so remember when we talked about the Froude number, and that the Froude number was equal to the velocity over the square root of G times the hydraulic depth, and that this is the velocity of the channel. This was the velocity of the celerity wave. Right, as those arrows keep plaguing me. So this is the velocity of a celerity wave. So if I drop a pebble in a brook and I've got some, or the water is flowing along there, if it's subcritical flow, this still has the ability to emanate upstream or translate upstream the disturbance, but because the velocity is not fast enough to keep it from doing that. But if it was supercritical flow, it would only emanate down, or it wouldn't emanate, it would only be shown downstream. So this says that if I'm in a subcritical range, I can have disturbance downstream that affects me upstream. So that's when we talk about the control. That's why we route when we do the modeling, we go from downstream to upstream in a subcritical flow. Whereas for supercritical, you feel the effects, what happens upstream, you feel them only downstream. You can't feel them upstream. So the other thing to mention here is that for this direct step method, it only applies for prismatic channels. Remember, prismatic says that the cross-section shape does not change, and it doesn't change in roughness and those kind of things. Can you think why this is so? If you look back at the direct step method, this is the loss, S sub F is the loss due to friction and friction only. And if we look at this equation, we have no ability, because as you know, we're going to have losses due to expansion and contraction in non-prismatic channels, right? So we can't really, because we have no mechanism in the equation to handle it, the only losses that we can account for are those due to friction. We don't have any ability to account for the losses due to expansion contraction. So let's erase this where you can see it. So this is what I was saying, is that in non-prismatic, we have to account for energy loss due to expansion contraction. Given we don't do that for the direct step method, it's only valid for prismatic channels. So if we look at a kind of a diagram, so we've got this channel, it goes off the edge of well, it's just got a big drop there. So we're going to go through critical depth at this end. And let's assume that this is subcritical flow. So we're going to route from downstream to upstream. And so what we're going to do in a direct step method is that we're going to know, you have to have a starting boundary condition. Starting boundary condition. And so on a subcritical flow, that's downstream. I have to assume something down here at the downstream end. So I'm going to, for this particular example, because I know that this drops off, I'm going to assume that this is Y critical down here. So I can compute that critical depth, and I can give myself a starting boundary condition here. And so then what I'm going to do is I can calculate the specific energy, E downstream there. And I'm going to say, okay, I know this depth. That's why it's important to kind of know something about the water surface profiles and what they should be. I know that this depth should increase, so I can calculate, I can just assume upstream here, let's say that this, just for give some numbers here, let's say it's 5 feet. And so I go upstream and I say, okay, well, here is 5.1 feet. How far delta X1 is it to go from 5 feet at this location to 5.1 feet? Because this is 5.1, I also am going to have to know the Q. That's going to be known. So from that, I know what the velocity is at this location, and I know the depth. So I got everything I need to calculate the specific energy upstream and downstream. And I'm also going to know the bed slope. That's S sub O right here. And then I'm going to calculate that average friction slope. So what I'm going to do is I'm going to calculate the friction slope upstream plus the friction slope downstream, and I'm going to divide that by 2. And so remember that we had the equation here that told us how, from Manning equation, we can calculate that friction slope. And so we've got what S sub F upstream is equal to 2.22 times V squared upstream divided by, let's look at that, is that 5/3? No, it's 4/3. And I got the 2.22 in the wrong spot. So it's in V upstream squared, 2.22, and then that's r to the 4/3 power. Okay, and so I can do that up, I can do that downstream. That's n times v down squared over 2.22 r down to the 4/3. And then I have everything I need to know in order to calculate this delta x, this distance from here to here. We're going to go through a direct step example next.